Assalamualaikum and a very good day to dear panel Dr. Muhammad Azmi Yunus and Dr. Muhammad Hanif bin Muhammad Ramli. My name is Muhammad Aziz bin Anas. Under the supervision of Dr. Abdul Halim Abdullah, would like to present my final year project, which is the effects of infill density, wall perimeter and layer height in 3D printing. These are the contents that I will go through during this presentation, from introduction until conclusion. 3D manufacturing or additive manufacturing is the process of making three-dimensional solid objects from a digital file. The creation of a 3D printed object is achieved using additive processes. In an additive process, an object is created by laying down successive layers of material until the object is created. Each of these layers can be seen as a tiny slice cross-section of the object. As Scott Crumb is the inventor of fuse deposition modeling and co-founder of Stratasys Limited. Crumb invented and patented FDM technology in 1989 with his wife and Stratasys co-founder Lisa Crumb. While 3D printing has been around for decades, it has surged in popularity and usage in recent years. New 3D printing applications are constantly being developed, but the applications detailed below have recently risen in popularity. The significant field that can be related to 3D printing in education, prototyping and manufacturing, medicines, construction, and art and jewelry. FDM 3D printing parameters can significantly affect the mechanical properties of printed 3D models, the amount of time taken to fabricate, as well as the amount of material used. Examples of parameters are infill density, wall perimeter, layer height, infill pattern, and others. In this study, the former three parameters were studied. What is infill density? The infill density defines the amount of plastic used on the inside of the print. A higher infill density means that there is more plastic on the inside of your print, leading to a stronger object. An infill density of around 20% is used for models with visual purposes. Higher densities can be used for end-use parts. What is wall perimeter? Each layer of 3D printed part is created using a combination of outline parameters and infill. The perimeters trace the outline of your part, creating a strong and accurate exterior. The infill is printed inside of these perimeters to make up the remainder of the layer. What is layer height? Layer height is exactly what it sounds like, the exact height of each layer of plastic extruded, cured, or sintered by a 3D printer. This setting is adjusted through a slicer program and has many more effects on the final print than one might think at first. Used properly, this setting will increase your print speeds, resolution, and smoothness. For past studies done by UA on the effects of infill density on the mechanical properties of 3D printed PLA and conductive effects of infill density on the mechanical properties of 3D print, this study aims to find out the optimal infill density of PLA and conductive PLA. For pure PLA, it shows an increasing trend in ultimate tensile strength as infill density increases and achieves highest in 100% infill. However, there is a decreasing trend present in conductive PLA as the infill density increases. The tensile strength for conductive PLA is generally 2 times lower than the pure PLA printed due to the presence of carbon. Other studies done by Rismalia M on the infill density and density effects on the infill pattern and density effects on the tensile properties of 3D printed PLA material. 3 infill densities, 35%, 50%, and 75%, and 3 infill patterns, grid, trihexagon, and concentric, were chosen. The tensile test or STM D638 was employed to obtain the material properties based on these two printing parameters. Young's modulus, yield strength, and ultimate strength were recorded and examined. The results showed that the tensile properties increases as infill density increases. Of the 3 printing pattern, the concentric has the highest value of the tensile properties regardless of the infill densities. For the problem statement of this study, increasing the settings of the parameters can lead to higher strength of parts. but this will result in a higher amount of material used and longer fabrication times. Therefore, finding the right balance between these factors can save costs and time, as well as having the reasonable strength of the parts. Mechanical properties of PLA for different parameter settings do not available yet. There are two objectives of this study, which are to develop 3D models of a tensile test specimen at different infill densities, wall perimeter, and layer height. Second is to predict the effects of the different parameter settings on the strength of the model. The scope of this study is to firstly set the parameter settings that wanted to be tested, establish the different settings for one parameter as the manipulated variable, and set the same settings for the other two as constant variables. For infill density, the settings are 0%, 20%, 40%, 60%, 80%, and 100%, while maintaining wall perimeter at 2 mm and layer height at 0.2 mm. For wall perimeter, the settings are 1 mm, 2 mm, and 3 mm. The infill density is set to 10%, while layer height is set at 0.2 mm. For layer height, the settings are 0.12 mm, 0.2 mm, and 0.28 mm. The infill density is set at 10% and wall perimeter is set at 2 mm. For the limitation of this study, it only tests one type of specimen type, which is the ASTM D638 type 1. The study only tests on one type of material, which is the polylactic acid or PLA. Next, only one type of infill pattern was tested, which is the rectilinear pattern. The first software used in this study is the CATIA V5R21. It is used to create models of a specimen of different parameter settings. The Ultimaker Cura 4.11 is useful to set the parameter of the 3D printed specimen and to use as a reference for creating 3D models on the CATIA V5R21. ANSYS Workbench R2 2021 was used to simulate tensile tests on different 3D models created earlier. This study has 6 main steps from the literature study until comparison computation that must be go through to execute them effectively. For literature study, the theory behind this study is the Young's modulus. The Young's modulus describes the elastic properties of a solid undergoing tension or compression in only one direction, as in the case of a material rod that after being stretched or compressed lengthwise returns to its original length. Young's modulus is a measure of ability of material to withstand changes in length when under lengthwise tension or compression, sometimes referred to as the modulus of elasticity. Young's modulus is equal to the longitudinal stress divided by strain. The second step is the development of 3D model in CATIA V5R21. Following parameters that have been set earlier. The estimation of dimension of the specimen was referred to the Ultimaker Cura. These are the 3D models for the different infill densities. There are 6 specimens with infill density of 0% up to 100%. For the wall perimeter, there are 3 specimens with settings of 1 mm, 2 mm, and 3 mm. There are no 3D models for layer height test due to the parameter can only be set on a 3D printed specimen. It is nearly impossible to set layer height in a 3D drawing. Next is the 3D printing specimen. Transfer the STL file of the 3D model of infill density at 100% into this software. This is because the Ultimaker Cura is a slicer software that can set the parameters of the 3D specimen before printing it. Thus, no need to import all the different models. Only a solid model will be sufficient. The file is then turned into G-code, saved in micro SD card, and slot into the 3D printer. The filament type used is A&V 3D PLA 1.7 mm 1 kg. The type of printer used is the Creality 3D and the 3 Pro. There are 3 samples needed for every 12 specimen, thus making 36 samples in total. The average time consumed in printing this specimen is around 45 minutes. The higher the parameter settings, the higher the amount of time it takes to print to. This will also result in higher amount of material and higher costs. Time is the only thing that can be reduced by using 3 printers to fabricate the specimen simultaneously at AA 3D printing. After all the samples have been printed, They will be tested their strength experimentally through the tensile test. The equipment used for the tensile test that was carried out in UITM is the Servo Pulsar Shimadzu Universal Testing Machine. The software used to control the feed rate of the UTM is the Servo A830. The feed rate is set at 5 mm per minute and with surrounding temperature around 25 degrees Celsius. For the computational analysis, the mechanical properties of PLA is taken from other studies were used as engineering data in ANSYS Workbench software. Convert the CAD file to IGS file and import the 3D models to ANSYS Workbench. Apply engineering data of PLA to the specimens. Select Auto Mesh for suitable mesh size on different models. Apply fixed support on one end of the specimen. Apply a vector force of 10 kN in the direction of the y-axis. Select data that wanted to be displayed, such as the maximum principal stress, total deformation, maximum principal strain, to be plotted into a graph, and run the static structural analysis. After the results have been generated, plot the data of the experimental and computational on Excel. Calculate the Young's modulus for each specimen and analyze the results. For results and discussion, based on the graph shown, the experimental stress strain data for infill density test among different infill densities of the specimen. The hypothesis for infill density is the higher the infill density, the higher the Young's modulus. The hypothesis is partially true but not entirely. In general, the pattern indicates that tensile characteristics rise as infill density increases. The stress strain shows that infill 100% has the highest curve, followed by infill 60% and infill 40%. At fourth place is infill 20%, and they are followed by infill 0%. Strangely, the second highest infill density, which is at 80%, has the lowest curve among other specimens. The product requires maximum tensile strength. It must be 3D printed with 100% infill. The second graph is the computational data for infill density test. The results that were run through ANSYS Workbench show the same trend of stress strain curve for the highest, which is at infill 100 for specimen 6. After that, it shows different results compared to the experimental. Infill 0% takes the second place and infill 20% takes the third place. The results were followed by infill 80% and infill 40%. Infill 60% is the last one on simulation stress data. The figure shows Young modulus for experimental and simulation for infill density tests. Between these two tests, the experimental test is the more accurate test and showed results that are closer to the theory or hypothesis, which is the higher the infill density, the higher the Young's modulus, although it is not 100% match. For experimental, from 0 to 20% infill density, there is an increase in Young's modulus. From 20 to 40% infill density, it reduces slightly, and then from 40 to 60% infill density, the Young's modulus rise. The Young's modulus then goes down from 60 to 80% infill density. The highest infill density, which is 100%, has the highest Young's modulus as well as the highest increment. This is due to each layer developing a strong link with the next layer at 100% infill density. The trend seems to be increasing steadily. This is not the case for simulation tests. The trend of the Young's modulus on the simulation does not follow a specific trend. From 0 to 20% infill density, the Young's modulus increases. The Young's modulus then increases slightly from 20 to 40%. From 40 to 60%, the increment of Young's modulus is the highest. There is a large reduction in Young's modulus from 60 to 80%. For the last infill density, which is 100%, the Young's modulus reduces a little. For the wall parameter test, both figures show stress strain curve for both experimental and simulation analysis, which are wall 1 mm, wall 2 mm, and wall 3 mm. In the experimental analysis, the stress strain data successfully follows the hypothesis of the study, which is the higher the wall diameter, the higher the Young's modulus. The specimen 9 at wall 3 mm comes at first place, followed by wall 2 mm, and the last one is wall 1 mm. However, in the simulation analysis shown, the stress strain curve does not follow the hypothesis. The trend seems to be quite the opposite, with wall 1 mm has the highest curve, followed by wall 2 mm, and the last goes to wall 3 mm. The figure shows Young's modulus of experimental and simulation for wall parameter tests. Like the infill density test, the experimental results of Young's modulus are also favorable to the hypothesis of the study. The trend shows the higher the wall parameter, the higher the Young's modulus. From the first specimen with wall parameter of 1 mm to the second one of wall parameter of 2 mm, the Young's modulus increases. The Young's modulus also increased from wall parameter of 2 mm to 3 mm. On the other hand, the simulation results of Young's modulus show differently. It shows the highest Young's modulus at the lowest wall parameter of 1 mm. It then decreases dramatically at wall parameter of 2 mm and rises slightly at wall parameter of 3 mm. It does not follow a certain trend. As with most early prototypes, the maximum strength of the product is not the most significant factor. However, using those data, a mathematical model that predicts the tensile strength based on the infill pattern and density can be built. The layer height test. There is only experimental data. The figure shows stress strain data for the layer height test. The strength of the stress strain curve follows the hypothesis of the study, which is the higher layer height, the higher the strength of the specimen. The highest curve goes to height 0.2 mm, followed by height 0. The highest curve goes to height 0.28 mm, followed by height 0.2 mm, and the lowest curve goes to height 0.12 mm. This curve shows a gradual decrease of the ultimate tensile strength, different compared to the infill at 100%, which snaps immediately after ultimate tensile strength. This shows that layer height affects the ductility of the specimen. The figure shows the result of the experimental layer height test. This test was only carried out experimentally, thus cannot be compared to other results. Results follow the hypothesis, which is the bigger the layer height, the higher the Young's modulus. Height 0.28 mm have the highest Young's modulus. The trend is followed by the second highest, which is height 0.2 mm, and the last specimen at height 0.12 mm. So in a nutshell, the study that has been carried out successfully met the two objectives of this project. All the 3D models of different parameters have been successfully created through CATIA V5 software concerning Ultimate Cura. For the hypothesis or prediction of the effects of the different parameter settings to the strength of the models, the trend of the experimental results majorly follows the prediction of the studies, which is the higher the parameters, the higher the strength of the specimen. On the other hand, the computational results deviates from the prediction of the studies due to the dimensional uncertainties of model and meshing difficulties and others. For recommendations in the future, use software that can set the parameters of 3D model and convert it to a CAD file instead of G-code to avoid dimensional uncertainties of the 3D model. Test the strength of different infill patterns such as honeycomb, concentric, triangular, and others. Test the strength of more materials such as ABS, resin, alumite to be compared their strength with PLA. And lastly, study the amount of material and the amount of time taken to print to the strength of the specimen. That's all for my presentation. Thank you.